Hello and welcome to the video on angles in alternate segments. In this video we will prove that the angle between a chord and a tangent is equal to any angle at the circumference in the alternate segment. Then we'll look at two examples using this property. So what does it mean to be an angle in an alternate segment? Let's say we have a tangent xy which touches a circle at P, and the chord PQ divides the circle into two segments. We call these two segments PQR and PQS. The segment PQR is said to be alternate to the angle QPY. An angle PRQ is the angle in the alternate segment corresponding to the angle QPY. Similarly, the segment PQS is said to be alternate to the angle QPX, and the angle QSP is the angle in the alternate segment corresponding to the angle QPX. Our theorem says that those two angles are going to be equal to each other. The angle between the tangent and the chord is equal to the angle in the alternate segment. So let's prove it. We want to prove two things: that angle QPY is equal to any angle in the alternate segment, and that angle QPX is also equal to any angle on the other side of the chord. We know that XY is a tangent at the point P to the circle with a center O. We know that PQ is a chord through P, and to help with our proof, we will need to draw in the diameter PR and join RQ to create a triangle. To begin this proof, we'll say that angle QPY plus angle QPR equals 90 degrees. We know this because tangents are perpendicular to a radius at the point of contact. We can also say that angle PQR is 90 degrees because of angles in a semicircle. Therefore, angle PRQ and angle QPR have to add up to 90 degrees. This is because the angle sum of triangle PQR is 180. We can now say that angle QPY equals angle PRQ, and we can do that. But angle PRQ is going to be equal to any angle PTQ because of angles in the same segment. See how they make butterfly wings? So therefore, angle QPY equals any angle PTQ in the alternate segment, which is what we wanted to prove first. Next, we are going to prove that it is also true for the other angle on the tangent. We say that angle QPX plus angle QPY will equal 180 degrees. This is because XPY is a straight line. So angle QPX is going to be 180 minus QPY. Drawing in the angle we just proved to be angle QPY, we can say that angle PTQ, which is the green circle, plus angle PSQ, the orange circle, adds up to 180 degrees. This is because they are opposite angles in a cyclic quadrilateral. Therefore, angle PSQ equals 180 minus the angle PTQ, which is the green circle. But angle PTQ equals angle QPY, which we proved in our first part. Therefore, angle PSQ is going to be 180 degrees minus angle QPY, meaning that angle QPX will equal any angle PSQ in the alternate segment. The trick to recognizing this particular property in pictures is to highlight where the chord and the tangent meet, and then highlighting any angle at the circumference that creates a triangle from that chord. Let's look at example 15. TE is a tangent to the circle. Angle DTE equals 55 degrees and angle GDE equals 83 degrees. Find the size of angle DGE, giving reasons for your answer. Take a moment to pause the video and try and work it out for yourself. The angle you are trying to find has been marked, and this just happens to be the alternate angle corresponding to angle TED in the picture. Okay, I can see that the 83 degrees is the exterior angle of the triangle DTE, meaning that angle TED plus 55 will equal 83 degrees. Therefore, angle TED is 28 degrees. But angle TED is equal to the angle DGE, the one that we're trying to find, because of our newly found theorem of angles in alternate segment. Therefore, angle DGE is 28 degrees also. Example 16 looks tricky and does use a few of the theorems we have seen in the past. It says that TB is a tangent to the circle with a center O. BC is a chord, and OA is the radius perpendicular to BC that intersects BC at D. We are asked to prove that AB bisects angle TBC. Take a minute to pause the video and come up with your own solution. They ask you to prove, so setting up a proof with an aim, data, and proof will be a good start. Also, consider the information they have given you. They wouldn't give it to you unless it was useful. unless they're trying to be cruel. And finally, they are asking you to prove that AB bisects angle TBC, but what they are really saying is to prove that angle TBD equals angle ABD. Good luck. Okay, setting out my proof, I begin with my aim to prove that AB bisects angle TBC, remembering that they are really asking me to prove that angle TAB and angle ABD are equal. I know TB is a tangent with a center O, and that BC is a chord. OA is a radius perpendicular to BC and cuts BC at D. I'm using congruence for this proof, so I begin in triangle ABD and triangle ACD. BC equals DC, because the radius perpendicular to a chord will bisect the chord. There's a theorem that we've used before. And I know that angle BDA equals angle ADC, because OA is perpendicular to BC. Also, DA is common. Therefore, triangle ABD is congruent to triangle ACD because of side angle side. Now we've proven that they're congruent, we can say that angle CBA is equal to angle BCA because of corresponding angles in congruent triangles. But we know that angle TBA equals angle BCA because of our new theorem, angles in an alternate segment are equal. Therefore, angle TBA is equal to angle CBA, and we have proven that AB bisects the angle TBC. The next video in the series will look at tangents from a single point and what properties that brings to us. Thanks for watching.